Okay, so hello everyone, welcome to the new session. And in this session, we will discuss a very important property of the real numbers, which is basically the property of completeness. Fine. So let me first give the heading. So we are intended to discuss the property of completeness. Fine. Now, the thing about completeness is that this is one of the main properties why the real number system was developed because the rationals was till that point of time the rationals were the most useful number system. But the problem with rationals came due to the absence of this notion of completeness. Now, if you're already pretty much acquainted with the with real analysis, then this is the term is somewhat you have heard of somewhere somehow. But so our goal is to discuss the topic of completeness in this lecture and how what are the properties which it gives to the real number system and how one of the most important parts of real analysis, which is the study of sequences, is concerned about completeness. Right. So what is completeness basically? So if I just add the definition of completeness, so the definition of completeness is basically that any bounded set in R has supremum, okay, uh, and an infimum, or rather, let me be a bit more precise. Any bounded above set in set R has a supremum, and any bounded below set in R has an infimum. Okay. So these are the two terminologies which we need to get acquainted with. That is the notion of what a supremum is and the notion of what an infimum is. Right? Now, what is basically the supremum? So before formally defining what a supremum is, we need to understand the sense of it. Okay. When is a set? So suppose B is some subset of R. Okay. We say that B is bounded above if there is some real number which is greater than or equal to every element of B. Fine. That is the basic definition of being bounded above. And similarly, if there exists some real number which is less than or equal to every element of B, then we say that B is bounded below by that element. So, we can say alpha in R is an upper bound. So, upper bound is the element which bounds B from the top. Okay. So, alpha in R is an upper bound for B if for every B in B is less than or equals to alpha. Is it clear? And in this case, we say B is, so in this case, we say B is bounded above. Fine. Now see, by the well ordering property of the reals, this can be pretty easily understood that if I choose any real number which is greater than alpha, greater than or equal to alpha, that will still be an upper bound, right? Now for every beta greater than or equals to alpha, beta is still an upper bound for B, right? It is pretty easily understandable. It is still an upper bound for B, right? Therefore, I can consider a collection of all these upper bounds, right? Which is sort of ordered by you can start with the element alpha and you can keep taking real numbers which are greater than or equal to alpha. So therefore, we can have a well-defined collection of these upper bounds. A well-defined collection of these upper bounds. Fine, got it. So let MB, the collection of all alpha, real numbers alpha, such that alpha is an upper bound of B. Alpha is an upper bound of B. Right? So we take up this set. Now, what is supremum? So the supremum, so this is one terminology, the supremum or the least upper bound, which is what the name suggests, is the least element of all the upper bounds of all the existing upper bounds. So the supremum of B, because we are talking relative to B, so the supremum of B is the least element of all the upper bounds of B. That is, we can also talk it in this way, that it is the, in some sense, it is the minimum of all the elements alpha in A. Fine, you're getting my point. Now, the precise fact here is there is a certain abuse of notation here, because I cannot talk about a minimum here because there are infinitely many elements in this case, right? So the mathematical term minimum is not that well defined in this case, but the sense is clear, right? So what we are doing is that I'm choosing a set and I'm given that there exists a real number which is greater than or equal to every element of that set. Fine. That element is what we are calling an upper bound. Fine. Once we have an upper bound, I am talking about all possible upper bounds of that set. And I'm taking the least element of all these upper bounds. And that least element of all these upper bounds will be called the supremum of that set. Fine? Okay. And now it is obvious that you are not sure whether such a minimum element exists or not, right? Like in case of natural numbers, we know that if I choose any subset of the natural numbers, it will always have a least element. That is not precise in case of real numbers, right? Because it is not bounded below. The real set is not bounded below. But it is made to be a property of the reals. And that's where the importance of reals comes in hand. Okay. The construction of reals is done, the real number system is done in such a way that every set which is bounded above, that is some upper bound exists, it will always have a supremum. That is exactly what the completeness property of the reals state. Fine. So now we always have this supremum in R. Getting my point? And the same sort of an argument you can apply for a set which is bounded below. Fine. So if I have, so let me just do it very briefly. So suppose, beta is less than or equals to B for all B in B. Then I can similarly talk about the collection of all these lower bounds. So this will be called a lower bound. A lower bound for R. Lower bound for B. And I can talk about all possible of the, all possible lower bounds of capital B. And then I will need to take the largest of these possible lower bounds. Okay. So the largest of all these lower bounds will be called the infimum, or as the name suggests, the greatest lower. Fine. So now let us go back to the property of, so I guess you guys have somewhat understood how it works. Let me just talk about a very brief example. For example, suppose say let B mean R such that B is the collection of all those points such that the square is less than 2. Fine. Or let's say less than or equals to 2. No, won't cause a problem. No, let it be, yeah, it will work. Right? Okay. Now you can easily see that, or rather, let us not talk about this example because this actually needs a bit of rigorous work. I'm not concerned about the rigorous work at this point of time, but we need to understand the sense of supremum and infimum. So a very simple example which we can talk about, for example, any maximum is a supremum. Okay. For example, suppose this can be a very sense-making example at this point of time. Suppose B is say 1, 2, 5, 6, 3, 2, and it is in R. Now you can easily observe that 6 is a real number which is greater than or equal to every element in B, right? And 7, 8, 9, 10 elements in between 7 and 8, 8 and 9, 9 and 10, so on and so forth. Every real number which is greater than or equal to 6 will still act as an upper bound. But you can observe that if you go to any real number which is less than 6, if alpha is a real number which is less than 6, it will no more act as an upper bound for this set B, because 6 is an element of B, right? So if alpha is less than 6, then this immediately means alpha is not an upper bound. Alpha is not itself an upper bound, right? Alpha is not itself an upper bound, right? Therefore, 6 is the least possible upper bound for this set, and that will be defined to be the supremum, right? In some sense, if you are given a finite set, then you can always talk about the supremum being the maximum of that set. And in a similar case, you can just work out that 1 will be the infimum, which is basically the minimum of this set. Fine. Right. So I hope you guys have got an overview of what supremum and infimum looks like. We can briefly talk about the formal definition. So we will cover the formal definition at this point, and we will furthermore talk about the completeness property once more. Right? So the formal definition, let B in R be a set such that there exists some M in R such that M is greater than or equals to B for all B in capital B. Then M is called an upper bound for B. Alpha in R is called the supremum of B if, point number 1, alpha is an upper bound. That is the obvious criteria which we need to look for. So alpha is an upper bound. And number 2, if let's say beta is some other upper bound, then alpha should always be less than or equals to beta. Fine. What do I mean by this? So this formal definition actually gives you the fact that alpha is the least element of all the upper bounds, because first of all alpha is an upper bound, so that's fine. If beta is any other upper bound, then that needs to be greater than or equal to alpha. That immediately means that alpha is the least possible upper bound, and hence it makes sense. And similarly, you can talk about the infimum by just taking an element which is a lower bound. You need to talk about a set which is bounded below, and so you need to talk about an element which is a lower bound, and you need to take the maximum of that, of all those lower bounds, the largest of all those lower bounds. That will work out as the largest upper bound. So I mean the greatest lower bound. Fine. Right. Yeah. And the completeness property, as I stated. So the completeness property states. Now we say a set is bounded, simply bounded, if it is both bounded above and below. Okay. So the completeness property of R, it says that every bounded subset of R has a supremum and correspondingly an infimum. Okay. So given a bounded set, it will always have a supremum as well as an infimum. Got it? And that's the important property of the real numbers. This is a property which is not for the rationals. Okay, the rationals are not complete. Right? R, in some textbooks you will find to see that R is, the unique. R is a unique, complete, ordered field up to isomorphism. Okay, this is a standard quote you will see it in every standard textbook, that the reals is unique, complete ordered field. I'm not going to get into the details of what we mean by an ordered field up to isomorphism. Okay. So in very simple sense, it means that R is in some sense the only field. Uh, you know, field is the algebraic terminology field. The only field which is both complete and ordered, and it's up to isomorphism, right? That is, if there exists any other such structure, then that element wise, or rather property wise, that should be exactly same as the real. So yeah, so that's the overall sense it makes. Q on the other hand is ordered, is an ordered field. It's not complete. Is not complete. And why is it not complete? We will come to this once we introduce how supremum and infimum are related in terms of sequences. Right? So let us quickly get into that. So sequences. Now assuming that the basic definition of sequences is known to you. So yeah. So these are the thing properties which we somewhat already know. That suppose xn is a real sequence. That is, xn is a sequence in R. So xn is a real sequence which is bounded, and monotonically increasing. Okay, which is bounded and monotonically increasing. What do we mean by this? Let me just clear out the facts. So by bounded we mean the exact definition that there exists some positive m such that mod of xn is less than m for all n. That is, every element in terms of magnitude is less than m. Fine. And what do we mean by monotonically increasing? That is, xn is less than or equals to xn plus 1 for all n. That is, the terms of the sequences are gradually increasing. Okay, as the indexing set is increasing. In some sense, it typically means that, right? So, so suppose xn is a real sequence which is bounded and monotonically increasing. Then, what we claim is that a sequence xn converges, and it converges to the supremum of the collection xn. Okay, here we are treating xn as a sequence, here we are treating xn as a collection of elements. For example, suppose I have this sequence, say 1, 2, 3, 4 and so on. Okay, suppose I have this set and I have this sequence 1, 2, 3, or rather I have this sequence n. Okay, so here we have the elements as a sequence, and here we are just treating the elements of the sequence as a set. That is exactly what I mean by the difference of these two notations. Right? Yeah. So this is my claim. So what am I typically claiming is that if I have a real sequence, you need to focus on it being real. We will come to the fact that why we need it to be a real sequence, and this will eventually lead us to a very funny, or rather a very important conclusion. So suppose xn is a real sequence which is bounded and monotonically increasing. Then we claim that xn converges. Obviously, an arbitrary sequence, there is no guarantee that it will converge. But given a bounded and a monotonically increasing sequence, I am claiming that it will converge. And it will converge to the supremum of the elements in the sequence. Fine. So let's first try and prove it out. We will prove it step by step. Proof. Okay. So what is given to us? Given xn is bounded and xn is monotonically increasing. Fine. Now since xn is bounded, therefore by the completeness property of reals, the collection of elements of the sequence has a supremum. Right? Therefore, it sort of makes sense to claim that the collection of elements will converge to the supremum, because we conclude that the supremum indeed exists. Okay, so let this supremum be x. Okay, say x. Now we want to prove that xn converges to x. So what do we need to prove in order to show that xn converges to x? Our basic delta epsilon proof. What does it prove? So it gives the fact that for all epsilon greater than 0, okay, we are talking about sequences. I do not need the delta epsilon proof. What I need is the, what is called the definition of convergence in this case. So for all epsilon greater than 0, there exists some natural number such that whenever n is greater than or equal to this natural number, xn minus x in modulus is less than epsilon. The simple sense behind this definition, it means that xn is eventually, that is after some point in the sequence, is eventually arbitrarily close to x. Okay, that is as the number of terms in the sequence gradually increases, xn becomes closer and closer and closer to x. That's what we mean by xn converging to x. So we'll make use of definition to prove this. Now see, now there is a very important property of supremum, that is, so let me just state it once more, star if B is a bounded set such that alpha is the supremum of B, this is the notation used to denote a supremum, then for all epsilon greater than 0, there exists some element B in capital B such that alpha minus epsilon is less than B is less than alpha, less than or equal to alpha. If there is a problem in understanding this definition, the basic sense this definition makes is that is simply that alpha is the least upper bound. That if you go below alpha, you cannot have an upper bound. That is exactly what this statement means. Okay, not alpha minus beta, alpha minus epsilon. Alpha minus epsilon. So what do I basically mean is that suppose this is my alpha and suppose this is my set B in some sense, and we know that alpha is the least upper bound, right? So if you move even arbitrarily a little bit to the left of alpha, you will get an element which is alpha minus epsilon, but there will always be elements between alpha and alpha minus epsilon. That is, there will always be elements in capital B such that B is greater than alpha minus epsilon, which means that alpha minus epsilon cannot be an upper bound, and that is exactly what it means. Okay, so it again just clarifies the fact that alpha is the least upper bound. If you go to any real number which is less than alpha, even a little bit, it won't be an upper bound. Fine. So we will make use of this, okay, this statement. Now let us get back to the proof. So the proof continues. Yeah. So yeah. So now, since x is the supremum of these xn's, right? Therefore, there exists some n in natural such that x minus epsilon, this is less than xn, which is less than or equal to x by exactly the same property. Fine. Okay. Now let us go on to the next page. Now let small n be greater than or equal to capital N. Since the sequence is monotonically increasing, therefore xn must be greater than or equal to x capital N, but x capital N was greater than x minus epsilon. Fine. But xn will be less than or equal to x, right? Why does this hold? Since x is the supremum, so it's an upper bound of all these xn's, so it is the supremum of all these xn's, right? Fine. Because it's, and we do not even require it being a supremum to have this inequality, because we just need the fact that x is an upper bound of xn, right? But then this is less than x plus epsilon for every epsilon greater than 0 as assumed, because x plus epsilon won't be equal to x at all because epsilon is a positive number, and thus therefore we conclude. So what do we conclude? So we conclude that for all epsilon greater than 0, there exists some n in n such that whenever n is greater than or equal to n, xn is less than x plus epsilon and is greater than x minus epsilon, which means that xn minus x, this is less than epsilon, greater than minus epsilon. That means that modulus of xn minus x is less than epsilon. And therefore, by our definition of convergence, thus xn converges to x. Fine. So we can see that there is a very intricate property between convergence of some specific sequences and the existence of supremum, and the existence of supremum is quite necessary in this case. And this will serve as an example. Example. Okay. So what does the example specifically say? Suppose xn is a rational sequence. Xn is a rational sequence given by. So how do we define this sequence? So we define given recursively. That is, every alternate term is defined in terms of its previous term. As x1 is equals to 2 and xn plus 1 will be 1 upon 2 xn plus 2 upon xn. Okay, this is a sequence given to us. It's a well-defined sequence. There is nothing difficult in understanding that this is a sequence. And in fact, this is something I'm giving to you as a fact, but you can re-verify it yourself, and it is quite visible from the definition of the sequence itself that every term is a rational number. Fine. In fact, you can try and claim that this xn is it or rather let me treat it in this way. See, you can actually sort of prove this, that xn or rather xn is a monotonically decreasing sequence. I'm not going into the details. It's a monotonically decreasing sequence, and it converges to root 2. It converges to root 2. Now this is something which you can verify, that why does it converge to root 2? Suppose xn converges to some L. Okay, it's a monotonically decreasing sequence which is bounded. Okay, I am talking about a monotonically decreasing sequence here. So the same proof will work, but in this case the sequence must converge to its infimum by the same set of steps. It's quite easy to observe, right? Suppose xn converges to L, but that immediately means that xn plus 1 will also converge to L, right? There's nothing problematic in that. But then, if I apply limits on this term of the sequence, I can eventually claim that L is equals to half times L plus 2 upon L. So this implies that 2L is equals to L plus 2 by L, which means that L is equals to 2 by L, which means L is equals to plus or minus root 2. We won't take L is equals to, L is not equals to minus root 2, because the exact reason why L cannot be equals to minus root 2, because every term in the sequence. These are some intricate details which are covered, if you thoroughly study sequences, but these are just taking to be facts. Every term in the sequence is non-negative, in fact positive. Fine. And limits of sequences, they obey inequalities. That is, if an is less than or equal to bn, an and bn are two different sequences, and if both converge, then the limits will also obey the same inequality as the terms do. Fine. So L is equals to minus root 2. Fine. So yeah, so L, I cannot choose L to be minus root 2, so L must be equals to root 2. But the problem here is that root 2 is not rational. So this is not a rational number. Right? This is not a rational number. So a sequence which actually seems to be converging to some point will be declared to be divergent, or rather not convergent, if you are simply concerned about the rational numbers. Right? Therefore, I need to get hold of a number system in which such sequences must converge, which seems to converge, must converge, right? And that's why the completeness property comes in use, because the previous statement which we had proved, which is basically called the monotonically increasing sequences converges to a limit. I think it's called the monotone convergence theorem. Yeah, it's called the monotone convergence theorem. And so the monotone convergence theorem, it is exactly, it exists because of the completeness property. And you can see here that Q does not obey the completeness property, because if it would have obeyed the completeness property, then this sequence would have converged to some point which is the supremum of the collection of the elements, and which should have been rational. Getting my point? So yeah, so what we conclude here is that Q is not complete. Fine. So let us just summarize what all we did in this lecture. Number one, completeness property. Completeness property. Number two, supremum and infimum. MCT, which is the monotone convergence theorem, and Q is not complete. Fine. So yeah. So that's it for this session. We'll meet you soon.